It's my pleasure to introduce Matthias Seiß, who will talk about differential invariance of and the classic groups. So please.
Yeah, thank you for inviting me and introducing my talk. I want to say that this is joint work with Daniel Roberts. Right. So during my talk, I will focus on one of the classical groups of Lie rank L and its Lie algebra. And I want to talk today about orbits in the Lie algebra under gauge transformations by the group. Let me motivate this, why I'm interested in this question. So some time ago, I made the following observation. So for, well, as I said, a group G of Lie rank L and L differential indeterminates, I found in the Lie algebra a matrix, AG depending on P, such that it defines over the differential field generated by these indeterminates P a Picard-Wesset extension with Gara group G. So this matrix AGP is chosen according to the geometrical structure of the group and of the Lie algebra, which means that when we choose a root space decomposition, this matrix A0 plus, this is simply the sum of basis elements corresponding to the simple roots. And here in the second sum, we parameterized L root spaces corresponding to L specific negative roots gamma I. So here, this is the parameter. And down here, I have an example how these matrices look like in the case of the special linear group and in case of the symplectic group, where the representation is in case of the special linear group of dimension 4 and in the other case of dimension 6. So for the special linear group, you see that it has almost, or it has the shape of a companion matrix, but here you have a 0. And in case of the symplectic group, it has the parameters on the anti-diagonal. And the colors indicate which entries belong to which simple root. All right. Yeah.
May I ask short clarification? So in the theorem, G is an algebraic group, right?
Yes. Yes.
Yes. And yeah. By Lie rank, you mean the dimension of the space where the roots live. Right? So the dimension of Cartan subalgebra.
Exactly, it's the dimension of the Cartan subalgebra.
Yes, okay, so yeah. It's less than the dimension of the group.
Exactly. So in this case here, this is Lie rank 3, and here is it's also
and capital C are complex numbers, or is just some
algebraically closed field of characteristics 0. Yes, you can think about the complex numbers. Yeah.
Okay, thank you. Thank you. Just to make sure we understand the notation. Thank you.
Okay, so then these are parameter equations. They define a family of equations, and I'm interested in the question for which Picard-Wesset extensions are these equations generic? Yeah. So giving any Picard-Wesset extension with defining matrix, let's say in the Lie algebra of the group, is there a specialization of my parameters such that the specialized equation defines this extension? So let's shortly, a related question to this is the existence of a general extension field for these equations. So what do I mean by that? There are a well-known example in differential geometry for a general extension field. That's the general equation for the general linear group. And how do we start there? So we start with n differential indeterminates and look at the field generated by them. And on this field, we define the action of the general linear group. This is induced by right multiplications on the Wronskian matrix. And we look at the fixed field under this action. And our general extension field then defines a Picard-Wesset extension with Gara group, the general linear group. And the fixed field is generated by the coefficients of the equation, which are differentially algebraically independent over the constants. So the question here then would be, can we do a similar construction for our equations of the theorem? Meaning, can we start with a general extension field? And in this case, the differential indeterminates P then will be differential polynomials in the indeterminates of the general extension field. So I don't want to talk about this right now. The answer is yes, you can do something like that. We can talk about this later in the second half, and I have prepared a maple sheet where where we can compute some examples for the special linear group and the symplectic group. Okay, well, if you keep in mind the general linear group, it's clearly generic for every Picard-Wested extension that's defining matrix in n times n matrix by the cyclic vector theorem, right? So cyclic vector theorem guarantees us that we can gauge transform it to the shape of a companion matrix, and then we can plug into the y's, the n linear independent solutions, and everything spatializes down. So the question here, if you keep in mind how the defining matrix looked like in case of the symplectic group, is when is our construction generic, and giving a matrix A in the Lie algebra, which defining a Picard-Wested extension, then our construction is generic for this Picard-Wested extension if and only if we can gauge transform the defining matrix to our shape, to the matrix of the theorem of the first slide. To answer this question, when this is possible, one needs to analyze the orbits in G under gauge transformations by G. Okay, that's what the talk is about. We can first have a look to the algebraic case. So what is done in the algebraic case when we don't have a differential field or just the field C of constants. This is done by Bertrand Constant. And then everything becomes just the adjoint action of G on the Lie algebra. And you can then look at the polynomial functions on the Lie algebra, and the action induces an action of the functions, and you can consider the ring of G invariant polynomials. And it's proved by Chevalier that this ring of invariant polynomials is generated by L Lie rank many generators, which I denoted here by phi. And then Constant proves when he looks at the set of all maximal orbits or orbits of maximal dimension in the Lie algebra. So the maximal dimension of the centralizer is the Lie rank. So these orbits have dimension dimension of the Lie algebra minus the Lie rank. And then the invariant functions, they induce a map on the set. So this is here under point 1. We have a map of the orbits of maximal dimension to C of the power L, and this map is a bijection. Okay, so our invariants phi, they separate the orbits. Then he proves something else. Here we have mathfrak A, which is the centralizer of this element A0 minus, and A0 minus means just the sum of the basis element corresponding to the negative of the simple roots. So this is an L-dimensional subspace, and then he defines the L-plane mathfrak V just as the translation of A by A0 plus. Recall that was the sum of the basis elements corresponding to the positive roots. So then he shows that each orbit in O intersects this L-plane V in one and only one point. So let me draw a picture. So if this is a Lie algebra, and then here you have matrices defining orbits of maximal dimension, then the set V is just this line here. So this is V. And well, if you have any matrix and look at the orbit, then the orbit intersects this line only in one point. So something like that cannot happen. Yeah, so this is not happening. So why is this interesting for us? So first of all, it would be nice to have something similar with separating invariants. And the second reason is Costan said that here for this L space or linear space of dimension L, you can choose also something else satisfying two conditions. And the thing now is that we can also choose for this space the root spaces. Okay, this is the algebra gamma I. So actually, we can choose yeah, the set of all of our equations of the theorem of the first page. Yeah. Okay. So if we have a trivial differential field, somehow our equations are fine, right? Okay. So yeah, the question is, can we obtain a similar result in the differential case? And here we have first results for the spatial linear group and the symplectic group, so for the series. And yeah, let us just look at a little example how we can obtain something like that. So here we look at an element A of the Lie algebra of the special, of SL2, of SL2, yeah. The root system here is of type A1, right? We have simply two roots. This is alpha 1 and alpha and minus alpha 1. Okay, this is phi. And V represents alpha 1 and S represents minus alpha 1. And D is a parameter for the Cartan subalgebra. And now we look at a general element of the set U, meaning that the function V cannot become 0. All right, now we can gauge transform this matrix A to a matrix of the shape of our theorem by gauge transforming first with an element of the torus. You use an element of the torus to normalize the V to 1. And then you gauge transform with a root group element corresponding to the negative simple root to get rid of the component in the Cartan subalgebra. And what you get is this matrix, and this is SL2. Yeah, from I write phi because now phi, I define the rational function as the entry here. Yeah. Well, so this is good because we have kind of an algorithm which transforms an element of an open set of the Lie algebra of SL2 to our normal form. And what we can also verify is that the function phi is an invariant under the gauge transformations on A by the Borel subgroup. Okay, so we have an algorithm and an invariant. That's good. I think I'll show you this, that is really an invariant later on in Maple. The question now is, can we this extend now to the whole series and to every classical group? All right. So we call a matrix N in the Lie algebra to be a normal form if N lies in our L plane. So again, here A0 plus is the sum of the simple roots. And here this are the one-dimensional root space corresponding to the roots gamma I from the first theorem. Okay, or in other words, so a matrix is said to be a normal form if it has the shape of the first theorem. Yeah, we constructed or designed an algorithm which transforms a matrix A of a specific subset, mathcal X, of the Lie algebra to a matrix in normal form. Yeah. Oops, to matrix to matrix N, and A is gauge equivalent to this matrix N. Yeah, so let me explain how this algorithm works, and the best thing is to explain it by an example or by two examples. The first example is the transformation for the special linear group SL5, and this group is the root system is of type A4, and what I've drawn or painted here is the root system. So on the left you have all negative roots, and on the right you have the positive roots, and here in the middle this H1 up to H4 in orange, this represents the Cartan subalgebra. So somehow that's a mixture between the root system and the root space decomposition. Yeah, so we can also say, well, H1 up to H4 represents the Cartan subalgebra, and the roots represent the one-dimensional root spaces. So when we look at the right, I have done kind of a filtration of the roots. So in blue, you have all roots starting with alpha 1. In red, you have all roots starting with alpha 2. In green with alpha 3, and last but not least, alpha 4 in pink. Okay, so the first part of the algorithm transforms a matrix A to pre-normal form. I'll say what this means in a second. But first of all, let's have a look how this works. So assume that the highest root here is non-zero. We use now this root as a pivot element to delete all other roots in the filtration, meaning all blue roots in the filtration on the right, and use a while group element to transform this pivot element here to the simple root. Okay, so how does this work? In the first step, we gauge transform by a root group element corresponding to the root minus alpha 4. So here the black lines, they indicate that you have to add or to subtract a simple root to get to the next root. So here you have to subtract the simple root alpha 4 to get to this blue root. So what we do, we gauge transform with this root group element, and we get a linear equation in this root space which we can solve. So it's a linear algebraic equation, so not differential relation, and we can solve this equation, and delete this component. So this component will become 0. All right. So the next step now is to gauge transform with a Y group element corresponding to a simple reflection alpha 4. This Y group element does the following: it swaps over these two guys. So this here is now non-zero, and this root over here becomes 0. Okay, so we continue now. This is now a pivot element. Now we gauge transform with U minus alpha 3, delete that one, again a linear equation, and then we conjugate with the simple reflection corresponding to alpha 3. This swaps these two guys over. This root becomes non-zero, and here we have a 0. Well, and now we continue. So U minus alpha 2 V1, meaning that this guy becomes non-zero and that one 0. Okay, so I have done this graphically on the next slide here. Black means the components are deleted at now 0, and a color other than black means it's non-zero. Okay, now we look in the second part of the filtration to the red roots. Yeah, and again we assume that this root here is non-zero. We gauge transform by U minus alpha 4, get a linear equation, and this for this root, solve it, it becomes 0. Use the Y group element corresponding to the simple reflection for alpha 4. This swaps over, this is non-zero, and this becomes 0. So now conjugating with this Y group element does not delete anything we achieved over here. So it simply permutes the black roots. Yeah. So yeah, we get every time better and do not destroy anything what we already achieved. So we continue now. So this becomes non-zero. Yeah, until we come to the simple root alpha 4, and then we go to the whole filtration down and come now to this situation where all components corresponding to roots of height greater than 2 are 0. Okay, so at the beginning of the algorithm, I said something about a set Mathcal X on which the algorithm is defined. I always said, okay, we assume that this root over here is non-zero, or that root over here is non-zero, and use it as a pivot element. When this is the case, this is the most generic case. We call this subset then, or locally, this open set by U star. But it can also happen that this guy here is 0, and this will be our pivot element, yeah, and so on and so on. And these open sets we denote by Mathcal U. Again, Mathcal U powered star is the most generic one, and the prenormal forms is lower star, meaning just the case as we have it here, that all components corresponding to root of height greater than 2 are 0. And the union of all of these sets, this is our set Mathcal X. Okay, so how does our algorithm continue? The next step now is to normalize the components corresponding to the simple roots. And we do that by gauge transforming with a torus element. This gives us then on the simple roots algebraic equations, algebraic polynomial equations. And yeah, we can solve them and become, yeah, and then the components become 1. So something I forgot mentioning, why is it always solving a linear equation and not a differential equation? That's because we are gauge transforming here always with negative roots, and the logarithmic derivative then comes in the root space, for example. In this case, and the root space corresponding to minus alpha 4. So the differential part is not in the corresponding component. Yeah? So it's purely algebraic. We don't need to solve any differential equation. Okay, so what we have here, we have higher polynomial equations, so there is not a unique solution. Yeah? But this doesn't matter. The next step now is to delete the components of the Cartan subalgebra, and we do this by gauge transforming with all roots of height -1. These are now the roots here in blue. And here we have 4 roots of height -1, and this gives us enough freedom to delete the complete Cartan subalgebra. Okay, again, linear equations, the derivatives, they are in the root spaces corresponding to minus alpha 1 up to minus alpha 4. So the next step now is to delete the root spaces minus alpha 1 up to minus alpha 3. How we do that? We gauge transform with the negative, or with the roots of height -2. So now here always the simple roots are the pivot elements. Yeah. So now we have, so the number shrinks. Yeah. So we have 3 roots of height -2 and 4 roots of height -1. So we only can delete 3 roots, and because the dimension drops, and we cannot delete the component in this root space. Yeah. So that's why in our equation we set here a parameter. And we continue like that until we get our normal form. Okay, so in case of the special linear group, this works on an open subset. So that's enough, right? It's big enough. In case of the symplectic group, we need, and sometimes, simultaneous cancellation. And so our that X on which our algorithm is defined is a locally open subset of the variety of the Lie algebra of codimension L-1, yeah, on this case of this Blackdish SP8, which is of type C4 of codimension 3. So let me explain how this works in this case, in the non-trivial case. So here we first have to assume that, again, we have our filtration of the positive root in blue, red, green, and pink. And we have to assume in this case that the highest root is 0. So here we have our first relation. And then we can again take this one as our pivot element and gauge transform, as I explained in the case of the special linear group, until here. So now assume this root is our pivot element. We gauge transform now by a root group element U minus alpha 2 to delete here alpha 1. And now this gauge transformation has also an effect on this root, yeah, using this one as a pivot element. And we need now that we have here a simultaneous cancellation. So this has also to become 0. And then applying the Y group element guarantees that that becomes 0. This is different from 0. This is now different from 0. And that one becomes 0. And we can continue. Yeah. Okay. Yeah, and the algorithm continues as in the case of the special linear group, and the normal form matrix looks here like that. Here, the colored one are the roots where our parameters are set in theorem 1. All right, so this is our algorithm. So that's okay. So we have a subset mathcal X on which we can transform to normal form. Yeah. So now we want to look at the orbits in this subset. Yes. And for that, we need first to see that it is stable under some group of G. It is not possible that it is stable under the full group G, but it will be stable under a parabolic subgroup. And yeah, so which parabolic subgroup is that? Let I be the set of simple roots alpha 2 up to alpha L, and Wi, the subgroup of the while group of G, generated by the corresponding simple reflections. And we consider now the standard parabolic subgroup with respect to I. Yeah, then we can show, using the geometrical structure of the group, meaning the Pujolt decomposition and the definition of our algorithm, that that mathcal X is stable under gauge transformations by I. Okay, that's good. Now, we define our differential rational function, as in the example for SL2, as the coefficients of the normal form when applied to a generic element of our Lie algebra. And we call these coefficients then a phi 1 up to phi L. These are differential rational functions. Yeah? These differential rational functions, they are defined on this subset mathcal U star, so on the most generic one, yeah. Because when we normalize the simple roots, we have to divide by the pivot elements we used to get there, yeah. So it's only defined on U star. And how can we define it on the whole set mathcal X? Well, we simply say it is we extend it to the set by saying, well, the value is the coefficients of x gamma 1 up to x gamma L in the normal form of these matrices. Okay, yeah, then we can prove the following theorem. taking two elements of the subset math cal X, then they lie in the same pi orbit if and only if the differential rational functions phi coincide for these two elements. How does the proof here works? So this direction, what you first need to show is that our algorithm normal form, returns the same normal form for A and for the matrix B dot A. Secondly, you have to show that algorithm normal form returns the same matrix. Oh, this is an end. Returns the same normal form for A and Wi dot A. Okay. And then you just put everything together. In the other direction, I think that's trivial because well, when they're in the same, when they have the same values, then they have the same normal forms, and the transformation matrices which appear in the algorithm normal form, they lie in the parabolic subgroup. Okay, so the phi's are invariants under the parabolic subgroups. And later on, we can look at a maple demonstration for the special linear group and for the symplectic group. All right, yeah. Then we can also look at a G orbit. So when we have an element of the Lie algebra, which defines a Pickard-Wessel extension with differential Gara group G, and O denotes its G orbit, then the invariance phi separates the pi orbits in O, and the normal form elements of O are in one-to-one correspondence with this variety over here. Okay. Yeah, so that's it. I think I talked a little bit more than half an hour.
Yeah, but okay, that's okay. Thank you very much. So well, it's good that you finished, the self-contained part. So now we have time for maybe like one quick question, and then we will have more time for discussion after the breakout rooms. Any quick questions right now? Just unmute yourself and ask. Okay, so and maybe just for me to clarify. So and you mentioned that after the breakout rooms you can show some like explicit calculations you had
Yes.
for. Okay, that would be great. Thank you. So yeah, now I think we can move to the breakout room discussion.
All right. First, let me tell you something about the generic or the general extension field. So how is this done? So yeah, keep in mind the example of the general equation for the general linear group. And now how to construct a general extension field for our equations of the theorem of the first on the first slide. So remember that we started with L differential indeterminates, and so our differential extension field must have the same differential transcendentance degree. So here we start with L differential indeterminates A1 up to AL. Now we attach to this field or Liouvillean extension. Okay, so how is this extension defined? Well, we use these Lie rank many differential indeterminates to parameterize the Cartan subalgebra. And then we add the sum of basis elements corresponding to the simple negative roots. So this then defines a Liouvillean extension, and a fundamental matrix looks like the following way. We have here an element of the torus, which depends on Lie rank many exponential and exponential, so E Lie rank many exponential, and these exponentials clearly depend on the parameters a1 up to al. And then we have an element of the maximal unipotent subgroup, and this one depends on elements v, and these v are integrals of these exponentials and successive integrals of these integrals. So this is a Liouvillean extension, and this E now, this is our general extension field. Yeah. All right. So now we use the Brühart decomposition, and our fundamental solution matrix should correspond to the generic element of the maximal double coset and the Brühart decomposition. So, you know, the Brühart decomposition here, G is a disjoint union of this double coset B, W, B, where V comes from the Y group. And in the Y group, there's a specific or special element, the longest element. And now our fundamental solution matrix should be with respect to this longest element. So we have here V max, and then we have here U, and this U, I write it like that, A tilde, is parameterized by m differential polynomials in A1 up to AL, and these, what is M? M is the number of positive roots. Okay, so this is now our fundamental matrix Y, and these elements A tilde are chosen such that the logarithmic derivative of AY is AG, and here we have then differential polynomials depending on A. Okay, how does the group act on this extension E? Well, it acts by right multiplications with elements of G and then recomputing the Brühart decomposition of the product. Yeah, so okay. And then, well, we get a similar result as for the general linear group. The fixed field is generated here by the coefficients of our defining matrix. So this is the theorem here below. Okay, let's have a look how this looks like for the special linear group and the symplectic group. So I have to do here a new share, I think. So where is Maple? Okay, now you should see the Maple code. Okay, so the general extension in case of SL3. So SL3 is of Lie type A2, so L is 2. And here I have a program which computes the normal form coefficients. So here, these one are the elements parameterizing the torus. You see they're depending on A1 and A2, the exponentials. And then here B1, B2, and B3, this is what I called in the theorem V. These are parameterizing the unipotent subgroup. And here, this is the differential polynomial for the second unipotent subgroup element. And these elements down here, these differential polynomials, these are the coefficients of the normal form. Okay, so let's check if these computations are correct. So here are the matrices for the torus. Here are the matrices for the unipotent subgroup. For the first one, for the first element of the unipotent subgroup, and here are the elements for the second one. And this is the maximal Y group element. And now I get my fundamental solution matrix. It's the product of the unipotent elements, the maximal Y group elements, the torus elements, and the other ones. Yeah, yeah, and then I can simply compute the logarithmic derivative of Y, and I get the shape of my matrix. Okay, we can do this also in case of SP4. So we compute the coefficients. again the elements for the torus, for the unipotent subgroup, the differential polynomials for the second unipotent element, and the normal form coefficients. Again, we can put up together our fundamental solution matrix. Maximal Y group element, and here comes the fundamental solution matrix. And we compute again the Breuer decomposition of it. Okay. So yeah, these are the computations I wanted to show you for the general extension field. I think, Alexei, now it becomes clearer what I mean. I don't know if you have a question you can ask. Okay, no question. Okay, so now computing the normal form matrix in case of SL2. Here the general element of the Lie algebra looks like this. This was the example, the first example I gave in the talk. And now we gauge transform this one to normal form. What do? We first normalize V1 by a conjugation with the torus. Oops. So yeah, here we solve. We substitute it in the result of the gauge transformation. And they have normalized it. And now we delete the part of the Cartan subalgebra by gauge transforming with the unipotent subgroup element corresponding to the negative root, the negative simple root, solve it and substitute it. And here we get then our invariant phi. Okay, let's check that phi is really invariant under the Borel subgroup. So here we have a general element of the Borel subgroup. We gauge transform A by this element. And now we simply substitute the corresponding entries of the matrix GTA into our invariant and simplify it. And here is the proof that it is really the same one. Yeah, just take the difference. Okay, and case of SL3, though here the matrix looks like this. First, we gauge transform to normal form, though the first thing is to use this as a pivot element and delete this component. So we gauge transform by U2 and the simple reflection W2, solve the linear equation, substitute, and now we deleted the right upper corner. Next one is to normalize the entries corresponding to the simple roots. We do this. And here we need to solve polynomial equations of higher degree. And we get this matrix. And now we delete the part in the Cartan algebra by gauge transforming with the negative simple roots. So he has to think a little bit. And now we arrive at the normal form. Okay, our invariant polynomials, differential rational functions, are now the coefficients here with the star. We define them, and now we check that they're invariant under gauge transformations of the Borel group and under the simple reflection corresponding to alpha 2. So first of all, under the Borel subgroup, gauge transform, we substitute. Simplify. And here the difference shows that it's really invariant. Okay, now we have to see that it's also invariant under the simple reflection V2. So we gauge transform, we substitute, simplify, And here's the proof that it is really invariant. All right. Yeah, so in the talk, I mentioned that in case of the symplectic group, we have to do all this on a subvariety of codimension 2 here. And the subvariety is defined by these two differential polynomials, Q1 and Q2. Q1 is simply V9 and Q2 is a little bigger one. And first of all, we have to see that the idle is stable under gauge transformations of B minus and the two simple reflections W2 and W2U3. So first of all, we look at the torus. Oops. Okay, we gauge transform A, substitute, and then here we take the quotient because Q1 and Q2 are semi-invariants. Yeah. Okay, is it invariant under the root group U2? Yes, it is. Another root group U3. Yes, it is. And now another root group U1. So Q1 is simply invariant. And now Q2, we have to show that it lies in the differential ideal generated by Q1 and Q9. So what we can do, we can substitute V9 equals 0 into A, and then see if it is invariant. And so it's also invariant under U1. Okay, and here come the simple reflections, V2 and W2 and W3. Okay, so we see that the set mathcal X is stable under the parabolic subgroup. Yeah, next one is to transform a generic element of this subset to normal form. And this is done here. So on every step, we go down the filtration. And here, when we now deleted that one, we simultaneously deleted this one. Yeah, this ensures the condition Q2. I'm not sure that I executed. Okay, and here we normalize. This already takes some time.
But yes, meanwhile, John is asking whether the Maple worksheets will be available online just to play with, or it's some work in progress.
I think I sent Michael a PDF version of the Maple sheet.
Ah,
okay. But yeah, because for the Maple sheet you need my programs.
Ah, okay, yeah, makes sense.
Yeah, so you see here I did this program to compute the root system, the Lie algebra, and the group, and so on.
I will post the PDF file on the homepage.
Oh, yeah, thank you, Michael.
Okay, so now it is ready. Yeah, and then we stop because when you then compute really the invariants, it takes some time. So we can, so Andy can wait for his lunch then.
Yeah, maybe let me ask a question meanwhile. So you have this invariance phi, right? Which like distinguish orbits.
Yes.
Right. Like I wonder whether there's some. So they're differential polynomials, right? So I wonder whether you can say something about them as like differential polynomials. they're nice, they're Wronskins, or they're something, because like going back to the classical groups, right? So the invariants, they're very structured, so right? So it's
Yes, they are homogeneous polynomials, right?
Yeah.
Yeah. So actually, these rational invariants, phi, they are not very nice. Yeah. So of course, for low rank, they look nice, or yeah, you can write them down. But for higher rank, they get really, really big and ugly. So perhaps it's an expression of other differential invariant functions, yeah, and expressing it as a relation in other invariant functions, it looks nicer. I'm not sure if this is the case, so that's something to think about. Yeah.
I see. And like let's say we look at the case of SLN, right? So and we vary n. So how do they roughly grow? So can one say that there is some kind of recurrence or something? So this like series of invariants with n growing. Can you say something about the series of polynomials?
So now they you get. So you mean if you can obtain the one for SL n plus 1 from the one for SL n?
For example,
kind of a recursion or something like that.
Yeah, of maybe of some of the previous ones. Like,
I don't think so. No, I think you have to do it for each group. They are different. Yeah.
Well, I think in general, when you compute rings of invariants and get these generators, the generators are not unique. Is that right?
Yeah, you can have different generators. Yes, yeah.
Right. So in your program, how do you decide which one you're using, and how would a different choice affect your computation?
So I obtain these by the algorithm, and yeah, it's so I think it's a nice question to see how you can express the ones which I obtain by the algorithm in easier ones. I think that's what you're asking, right?
Yeah, right. I mean, and also the error has some significance. I mean, it's not just a set of generators. It has to be some kind of maybe minimal in some sense.
Yeah, L is the Lie rank. Yes. Yeah, probably. I don't know. So in the algebraic case, well, yeah, the polynomial of the polynomial ring of invariants, it's generated by L elements. Yeah. So.
Right. And now in your program, do you verify that the invariants are independent?
No, actually, we did not do that yet. Yes.
Okay.
You're right. Yeah, we did not yet do that. But probably they
one
are.
Or two. I mean, if the number of invariants 1 or 2, of course, you can see that they are in some.
Yes. Because
when you have more, then it would be very difficult to tell.
Probably it's not so difficult. So because you started with a fully parameterized matrix A, so at the end, this differential invariant should always contain, let's say, linear the variable you started with.
Okay.
So how can I explain this perhaps a little bit? Where do we have? So here in case of SL3, so you see every entry here has its own differential indeterminate, right?
Right.
So now you transform, you use this one to relate that, and so on, and then you then this one swaps somehow over. But at the end, when you have the differential polynomials here and here, somehow yeah, they are still a differential indeterminate linearly there.
Yeah. So you're saying that the transformation that you're using does not affect the, well, let's call it rank, the rank of the, I mean, in terms of, well, the differential transcendent degree in some sense.
Yes, yes, exactly.
To
There will,
generate
I think,
population.
generate the phi's still will be differential indeterminates. Yeah.
Right.
Yeah.
And when you compute the differential invariance or the generator phi, how is that computation different from the one in the algebraic case?
Mhm. So in case of
Because of course the operations involve differentiation now, of course.
exactly. So I think in case of SL2, the algebraic invariant is simply this part, right?
Mhm.
Which somehow makes sense when you say, okay, everything is a constant now, and then the derivatives vanish, right?
Right.
And this remains. So
Right.
that's also something. But I think what's happening, it's always the algebraic invariant plus some differential part. Yeah.
So it does generalize the one in the algebraic case.
Mm-hmm. I think so. Yeah. Well, I have no proof, but yeah, I hope so, and I think so. Yeah.
Yeah.
Okay, so any other questions?
You know, when you do these computations with some differential indeterminates, and let's say you get some differential polynomials, you have to write it in some unique form. Is that correct? So that you can actually tell equality.
What do you mean with unique form?
Well, you know, you can, well, with differential polynomials, of course, there is a unique way to write it so that you can test equality. Well, never mind. I'll take back my question. Sorry.
Okay.
Any other questions? Okay, so then, Matthias, is there more demonstration?
No, that's it.
Okay, good. Thank
Yeah.
you. So yeah, good. Then, if there are no more questions, and Michael will post the PDF version of this Maple worksheet.
Mhm.
So let's thank the speaker again. And yeah, we're looking forward to see everybody next week at the talk of Natalie. No, I hope I pronounced that correctly. I will learn that by the time about model theory and exponential functions, I hope. Okay, then, yeah, thank you, everyone.
Thank you.
You